Hi, and welcome to the next lecture unit in the lecture chapter on support vector machines, where we want to discuss two simple algorithms for training the support vector machine, one algorithm in the primal and one algorithm in the dual. So in the primal, I'll discuss a stochastic subgradient based approach, and in the dual, I'll discuss, I guess, most of the ideas behind sequential minimal optimization, where we do something like a pairwise ascent, a pairwise coordinate ascent in the dual problem. Okay, so until now I haven't discussed at all how we can solve any of the optimization problems we have studied in the lecture units before for the support vector machine. So the first question is, should we actually solve it in the primal or should we solve it in the dual? There's a lot of papers out that try to attack it either here in the primal or in the dual, and in a certain sense it is not absolutely clear what is best. It actually depends a lot on how many observations you have, depends on how high dimensional your problem is, and these various approaches, they all have their own advantages and disadvantages. So usually, traditionally, support vector machines are trained in the dual, and this is why I also included the dual representation of the SVM here in the lecture. And therefore, we will also look at one optimization algorithm here at the end of this unit. But before I want to do this, I want to look at a quite simple technique that optimizes the SVM directly in the primal. I should also say that it's not super easy to create an efficient support vector machine solver. So this is why there are so many papers out that discuss further improvements or just simply different algorithms. So a lot of stuff has been tried, and I will only here in this lecture unit cover basic ideas and not complicated numerical extensions or heuristics to speed the thing up. Okay, so let us remember how the unconstrained formulation of the soft margin SVM looked like. So we had our sum here over the training data, our summed losses, and this L function was the hinge loss, which looked like that. And then we had a second additive component, which was our regularizer. And hopefully you're not confused, because I'm rewriting this here a little bit. So remember, normally we have this C constant here in front of this guy, and this was just one half. So I changed this a little bit. So I'm now using a gamma here, and I'm leaving out the C, but I hope you can immediately see that this doesn't matter, right? I mean, it doesn't really matter where I put the weighting constant. I have to hyperparameter optimize this anyway. And it doesn't really change whether I weight this here up or this guy. And the reason why I'm doing this is because the next algorithm is traditionally presented in this form. And the other thing is this form is actually what we have used before to write down our regularized risk minimization. So we usually put the control constant before the regularizer and not before the loss term. Anyway, so our F is simply our linear scoring model, looks like this. And it would be nice if we could now directly attack this with simple gradient descents, but as I discussed before, this L function here is not really differentiable, at least at one point, so we have to be a little bit careful here. So what are our options now? We could, for example, use these smooth losses that I discussed before. So for example, the squared hinge or the Huberized hinge, and then simply do gradient descent. This works. This is kind of the reason why these guys here are introduced. Well, I guess for this guy you can optimize even more efficiently by solving a linear system. But anyway, we could also then do gradient descent. Problem is, as I also discussed before, this will not really create a sparse SVM if we do not add extra tricks to the optimization. So I don't want to discuss this here. And the other option is simply to say, hey, okay, this is a non-smooth problem. There's a particular class of optimization methods which are directly made for these types of problems. And one of the most simple ones is subgradient descent. Or we could even do stochastic subgradient descent as a fast approximation for large-scale data sets. And there's a very well-known implementation or algorithmic variant described in the literature, which is called Pegasus. And Pegasus is for primal estimated subgradient solver for the SVM. And this is what I want to discuss here, at least the basic variant. And this works like this. So it takes our regularized risk here, and we now do the usual approximation for stochastic gradient descent. We simply approximate this sum here by simply considering only one single example. And now we have the usual advantages that we can work on large data sets or even on online streams where we step by step only load into memory and consider a single observation, do a gradient update with respect to this single observation, and then move on. We can see this as a stochastic approximation of the full batch gradient descent. And of course, you can also do mini batches if you want to. I'll only discuss here the one sample version. And the mini batch extension is as straightforward as always. So we now look at this guy here. So we basically here just have removed the sum. In front of this loss component part here, again, our f function is this linear scoring function. This is our hinge loss. What I now can do is I can compute the subgradient of this guy here, right? So as I said, it's non-differentiable, so we have to use a subgradient technique. So how can we do that? Okay, let's do the gradient of this guy here first. So this is very easy, right? So the gradient of this guy is simply lambda times theta. Now we have to do the subgradient of this guy here. So we can use something like the chain rule. So how about we first do the inner derivative? And I should also say that from now on, I'll only discuss the version without the intercept simply to simplify things a bit. So let's compute the inner gradient with respect to theta. So this is very simple. So this is simply going to be x, or xi here in this case, right? So this is the inner part of the chain rule. And then for the outer part, we have to now compute the derivative of this not completely differentiable loss function. So this is our hinge loss. So the hinge loss is going to be 0 if the label times the score is larger than 1, okay? So only if it's less than 1, something non-zero is going to happen. And in that case, we now have to take the derivative of this guy here, and the derivative of this guy here with respect to the argument, which is f, is simply minus y. So we have minus y, so the outer part from the chain rule, times xi, which was the inner part, and actually it's minus yi times this indicator function here for the outer part times xi, which is the derivative of the inner part. So this is now our subgradient. And that's it. I mean, we can now directly apply stochastic subgradient descent. So here's the usual loop. We pick a certain step size alpha, we pick a random index I, and now we simply apply this formula here by computing our new theta vector, by adapting the old one. So we simply take our old theta vector, theta t, and then because we do a descent, we subtract this guy here times alpha. And then the only thing that I'm doing here is I'm writing this down in two cases, so I don't have to write down this indicator function. Yeah? So here's the case where we have the label times the score smaller than 1. So that's in a certain sense the more interesting case, because then here this second component is active. And here we have the case where the label times the score is larger than 1. So you can basically directly forget about this. And maybe this is easier to see. Here we have the old theta t minus lambda times the step size alpha times the theta here from, which is the gradient component from this regularizer here. And here you have the more complex situation where we're also subtracting this guy here, so minus times minus becomes a plus. And the only thing that I did here is I reorder terms a little bit, so I actually combine the old theta t that we have to adapt in the gradient descent with the gradient component from this here, and then you can nicely again see that what we're doing here is because of this rich L2 penalty is weight decay, right? You can also kind of interpret this as do a weight decay first, and then you do the gradient step, subgradient step of your loss function. We discussed this before. And this is now the complete Pegasus algorithm. You could do this in mini batches, as I said. You potentially want to do something a bit more clever here for the step size, which I'm not going to discuss here. But that's already it, and that scales actually quite nicely, even on very, very large data sets. And it's a very simple and direct algorithm. Okay, now towards an optimization algorithm for the dual SVM. So the dual SVM, again, I'm simply copying this over here from before, no change until now. So we want to discuss a simple algorithm. So how about we try to solve this? I mean, what makes this a bit, let's maybe analyze this first here. So this has a linear component in the alphas here. It has a quadratic component in the alphas here. So in total, we have a quadratic form in front of us, multivariate one. We also have here box constraints on the quadratic form, and we even have a further linear constraint on the as a further further constraint. So that actually looks quite complicated, right? So maybe you don't know what to do here now. So how about we try to solve this with something that's super simple? I guess the most simple thing we could do is coordinate the ascent. So we're maximizing, so it's not descent, it's ascent. And this would mean we try to optimize the whole thing in one variable. Doing univariate optimization is always much simpler. So we optimize this, for example, in alpha 1 and keep all of the other alphas fixed, and then we kind of cycle through all of the different alphas and optimize again and again in different coordinates. Unfortunately, this doesn't really work here. And the reason why it doesn't work is because we unfortunately have this linear equality constraint here. So if we begin to change a single alpha, this thing here, so assuming we are currently in a feasible point, right? This immediately becomes infeasible. I mean, obviously, if the sum here is 0 and then we increase or decrease alpha, this becomes non-zero here and the constraint is valid. So this doesn't really work. What we can do something similar. The next best thing might be not to update exactly one variable, but two instead. So we're going to optimize the whole thing in pairs. So this is called pairwise coordinate ascent in the dual. So we initialized, for example, our alpha vector to a complete 0 vector. So this would be feasible, right? Because it would be okay here, would also be okay here. We can also maybe do something more clever. Doesn't matter for now, don't want to discuss this. And now in every iteration of the optimization, I will pick a certain pair, alpha I and alpha j. So two dual variables, and these I want to update. All of the other variables I'm going to keep fixed as how they currently are. And I will now optimize this dual problem here only with respect to these two alpha I, alpha j variables, while not changing anything else. So let's think a little bit about whether that's possible, how hard that is, what the implications of that are. So first of all, if I look at this guy here, like I said, this is a quadratic form. So if I only optimize this in two alphas, this is still going to be quadratic in the two alphas now, right? Because all of the other variables, or the addition of those, well, I guess I can keep it as it's still going to be quadratic, but now, simply on a 2D space defined by alpha I and alpha j. I still have these box constraints going on, but as the problem is now in a much lower dimension of only 2D, actually we'll see that it's basically just 1D, this is not so difficult anymore. I can basically plot the thing in the two variables and then understand what happens, and I'm going to do this exactly in a few seconds. The other thing we have to still consider, and this is always kind of the most annoying thing here in the optimization of the SVM dual, is this linear constraint here. So we cannot arbitrarily change our variables, because then again we are going to violate this here, assuming we are currently in a feasible point. But we can now see what we have to do with our alpha pair. So assuming we are currently in a feasible state, we can look at yi times alpha I plus yj times alpha j. And these here will sum up to a certain value s in the sum. And if we add all of the other alpha I times yi's from all of the other variables up, in the end it's going to be 0, right? We know that because we're assuming we're currently in a feasible point. So the only thing we now have to take care of so that we stay feasible is that when we change alpha I and alpha j, that the resulting sum of this thing here is always going to be s, because then at the end the complete sum is always going to be 0. So as long as we keep that constant here to s, this constraint is still going to be fulfilled. And these boxed constraints are simple, right? So we just have to additionally take care of that alpha I and alpha j never become less than 0, and they should also never become larger than c. This is also easy to check and to consider. And I guess you can also already see that we are basically here having now a one-dimensional problem in front of us, because this side constraint is basically only leaving us 1 degree of freedom. What we will do is we will now add something, for example, to the alpha I, make it larger, and then we have to change alpha j here for exactly the same amount in terms of an unsigned absolute amount. So the sign of the change now depends a bit on the labels here, the yi's and yj's. So remember, these can only be +1 or 0, 1. So for example, let's assume yi and yj are both positive. And we have here our alpha I, and let's assume we make this larger for 2 points. Then of course we have to subtract 2 from alpha j to balance this out, so the sum here stays constant. And if the two labels have the opposite sign and we increase alpha I by, I don't know, 3, we now have to we have to do the same for alpha j again, so the sum stays constant. And the other thing we have to watch out for is that we are also staying here inside of these box constraints. And I have now visualized this on the next slides. So assume that we are in a valid state, and our everything is feasible. And now we will choose a certain pair of observations. And yes, there are heuristics to do this quite cleverly to speed up convergence, which I will not discuss here. So we will now pick these two observations here. So these two observations, they still have a current loss. So you can see this easily due to the fact that here the yellow guy, that's even misclassified. So that's on the wrong side of the hyperplane. And here we have this blue guy. This guy is correctly classified. It's on the correct side of the hyperplane, but it's inside of the margin. So this guy here will have a loss which is larger than 1, and this will have a loss which is between 0 and 1. And I now want to optimize in terms of these two data points, which means I want to optimize the alpha 1 and the alpha 18, so the associated dual variables, or you could also say the associated Lagrangian multipliers. And I can also observe that because the labels of these 2 points here are opposite, I have to apply an equal change to both variables even in their sign. So as I said before, the change is going to be equal anyway in terms of the absolute value, but it's also now going to be equal in terms of the sign. So for example, I could increase both of these here. And we'll see that exactly this is going to happen. So I've copied here over our dual problem. Nothing has happened here. And this is also a simple copy of the plot from before. Also note that my regularization constant in this example is now going to be exactly 1. I just simply chose that. And what I've now shown here, so this is the interesting part on the left-hand side, is the following. So I have plotted the objective here, but only in terms of alpha 1 and alpha 18. So these are the two guys I want to change, right? And in the background, through the contour lines and through this color coding here, you can see how the objective looks like in alpha 1 and alpha 18, and it's a quadratic form. I guess that you cannot see from the plot itself, but at least you can see how the contour lines develop. And if you go from down here to up here, they become better and better and better. So if you cross these contour lines in that direction, you are increasing your objective because we're in the dual. Remember, we want to maximize. Now, we also have to consider that there are these box constraints on the alphas. So I have to constrain from below with the 0 for alpha 1 and alpha 18. And I have to constrain from above with C, which was 1 in our example here. So I have to constrain here from above and I have to constrain here from above, which means I'm not only allowed to vary inside of this rectangle, but I'm even more constrained, as you will see. So my current configuration, or parameterization of alpha 1 and alpha 18, I'm assuming is here on this red point. Now, the last thing I need to consider is this linear constraint. And this linear constraint tells me, I could also say directly this constraint here, this tells me that I can only move on this line where this sum is constant. And because alpha 1 and alpha 18 have opposite labels, well, I mean, it's even simpler. So this linear function here, this even has slope 1. So what this basically means is if you now change alpha 1 and alpha 18, for example, if you go from here to here, you change both of them, you increase both of them by the same amount. And apparently, if we increase both, that becomes better in terms of risk. Or well, I shouldn't say that, it's not risk. It becomes better in terms of the dual objective, which we want to maximize. So we have to increase both and not decrease both of them. So we increase, and actually would like to increase them even further if we're here. But if we hit that point, we're now on the boundary. So now these constraints here become interesting and active to us. So actually it is alpha 18, which is now 1, and we cannot increase further, so we have to stop here. And that's basically it. This is what we do to optimize a pair. So we optimize on this line here. We have to respect the box constraints, and we have to optimize on this line here as much as we can by not leaving the box. And you can take this a little step further, and then you basically arrive at an algorithm which is called sequential minimal optimization, SMO in short, which does exactly this. It just tries to make it as efficient as possible, and it exploits the fact, and I hope this is obvious, that we are basically solving a very low dimensional quadratic problem over box constraints, and that we can actually do analytically. So the thing is, it's two variables, but the two variables have this extra linear constraint. So if you look at this guy here in combination with this, so only two variables are of interest to us. We are only varying the thing here, the objective, in two variables, but we also have to respect this linear constraint. So you can basically write down alpha I in terms of alpha j, or you can basically write it down. I guess you can write it down in the change. Let's call the change, I don't know, small c. So this would be the increase that we apply to alpha I. And if you write down the optimization problem in this single variable and plug it into this guy here, this will become a quadratic form with one variable. And obviously this change that you're applying, you can easily also compute the box constraints of that, because simply if you make C too large or too negative, right, at some point these box constraints here for alpha I and alpha j will become constrained. So you now have a univariate quadratic function over an interval. And this is really, really simple then to optimize, because we can do this now analytically. I mean, there's basically only three things that can happen, right? Either we are and this here is going to be our interval, right, that we optimize over. And one thing that could happen is that the optimum of that parabola is inside of that interval. And then we would simply jump to that. We can analytically solve for that, jump to that, and we are done with this pair optimization problem. Or the optimum of the parabola is outside of this interval here. So it could lie here or it could lie here. In our case, it actually lies somewhere here. And in that case, we simply jump to the boundary towards the direction of that optimum. But this boundary point, we can also easily compute and we can check for it, right? Basically, compute the parabola point, check whether it's outside, compute the two boundary points, and then pick the best of the three, if the parabola optimum is actually feasible and allowed. And if we do that, potentially with a couple of with an extra heuristic to cleverly pick the pairs, then we really have SMO, and SMO is still one of the most efficient implementations for support vector machines at the moment. And here on the right hand side, I have kind of visualized the thing again. So here you can see our alpha 1. On the x-axis, you can see our alpha 18 here in the blue line. So you can see if we increase alpha 1, we also increase alpha 18. And here we have marked the point where alpha 1 is still okay. It's 0.5. So this is here, but alpha 18 has already become C. And here, this yellow line is actually our objective. So you can see this basically looks linear, but it's actually quadratic. And you can see how we then simply move from this point here to this boundary point and stop here. Of course, we would have liked to go on to somewhere here where the optimum of the parabola would be.